Hi all, it's Mr. Yeager for Physical Science. We are basically finishing up our thermodynamic unit on a short talk about basically what happens with phases of matter and energy. Okay? Some of this is review. The first two kind of slides are basically something we've done before, and then we're going to look at what are called heating curves that you're going to have to analyze. So, for phases of matter, what we have is, again, we already know there's solid, liquid, and gas. We're not going to involve plasma at all. And what we're interested in this unit is reviewing the idea of which state of matter has the highest energy, which has the lowest, and then as I change from one form to another, am I adding energy or releasing energy? So, we already know solids have the lowest energy. Solid particles just vibrate in place, while gaseous particles are flying around everywhere individually and have a lot of energy. So therefore, if I go from solid, liquid to gas, I must be adding energy to my matter, to my object, while if I go backwards, gas, liquid to solid, I have to be releasing energy. So as long as I know that solid is lowest, gas is highest, we should know whether I'm adding energy to get closer to gas or losing energy to get closer to solid. So with that in mind, we can then bring in the state changes. Just highlight it for some reason. Get rid of that. Sorry, it's going to probably act up here for a second. All right. So we got our phase changes. I know there's a lot to see here, but to review our phase changes, solid to liquid is melting, liquid to gas is boiling, gas to liquid is condensation, liquid to solid is freezing. We also have the double jump, solid to gas is sublimation, gas to solid is deposition. So as we just said, if I'm moving toward gas, I must be adding energy. So melting is a process where I'm adding energy to the object. Boiling is a process where I'm adding energy to the object. Gas to liquid, I must be losing energy. Okay, I must be releasing energy. All right. So based on the direction you're going, we can identify the different phase changes as ones that are adding energy or losing energy. With that in mind, we use the more technical terms endothermic and exothermic. All right? So we might be asking you, is melting an endothermic or exothermic process? Okay? Melting involves you going from solid to liquid, which means you must be increasing your energy. If I'm increasing the energy, that means it's endothermic. So endothermic is a process that gets me closer to a gas. So that would be melting, boiling, and sublimation. Those are all endothermic processes, okay? Whatever you want to say with it. All right, where energy is being added, heat is being added to the object. Exothermic has all of the phase changes where you go back from gas to solid. All right, that's where you're decreasing energy, where the object's actually releasing heat, which that seems weird because when something freezes, you might be going, I don't feel any heat, but technically, when it's freezing, you actually are getting some heat pulled out of the substance itself, okay? Refrigerators basically have to use this process where they're trying to pull the heat out, okay? That's why sometimes the back of fridges are a little bit hot because they're pulling all that heat out in order to freeze everything inside to keep it cold, all right? So it's important to understand which way we're going and whether we identify it as endothermic or exothermic. Remember, endo, in, meaning adding energy, pulling it in. Exo means out, exit. It's releasing that energy, pushing it out. Okay? For the last thing, I'm going to go back to just a blank slide. I'm going to redraw it. The last thing we have to analyze is what's called a heating curve. Now, all of these curves look the same, but will be at different temperatures. A heating curve is a graph. What you're going to see is it will be a graph of temperature on the y-axis, usually in degrees Celsius, and time on the x-axis. Okay? This can be in seconds, minutes, hours, whatever. Okay? Seconds, minutes, hours. What we should see on this is, let's say I'm doing a heating curve for water, which will be the most common one. Let's do a heating curve for water. For a heating curve for water, I'm basically going to show when does water change from ice to liquid water, and when does liquid water change into steam or gaseous water. So what I need is basically a couple of important temperatures. We should know, hopefully, the melting point and boiling point for water in Celsius. The melting point for water is 0 degrees Celsius. The boiling point is 100 degrees Celsius. Those are like the only two temperatures you need to have on your graph. So I'm going to have 0 down here at the x-axis. And I'm just going to put 100 up higher somewhere. Okay? I'm going to lower that a little bit, darn it. I'm going to have to color that back in a little bit. I do want it to be a little bit lower since I have the writing. Okay, so I'm going to put 100 right here. All right, so what happens is we basically start at 0 time, and let's say I start at, I'll start down here at -5 degrees Celsius. Well, I start adding heat to it over time. I should start seeing the line go up. There's a graph, the line starts going up. That's temperature. Remember, that's the energy, the average kinetic energy of the substance. At 0 degrees Celsius, that's where water melts. So I'm going to actually see a flat line for a little bit, and we'll talk about what that means. Then you'll see a line that goes up to 100, sloping, not straight up. Then it'll be flat for a longer time at 100, and then it should keep going up. Now, why does it look like this? This is showing me what state of matter I have at the different temperatures. And it also shows me the phase changes. When water is less than 0 degrees, basically down here, this is showing me where the object is a solid, where water is a solid. Between 0 and 100 degrees, water is a liquid. And between 100 degrees and above, water is a gas. So that is, and this is the same on any substance. All the substances look like this, the same upward curve, flat line, upward curve, flat line, upward line. The only difference will be the temperatures that you might see on the sides. Not all substances melt at 0 degrees. Not all substances boil at 100 degrees. All right? But the bottom part, under the lowest slope line, is always solid. The middle slope line will be liquid, and the highest slope line is gas. And again, they might not be the same sizes as this, but that's how it's always set up. So what's happening here? At 0 degrees Celsius, I'm changing from solid to liquid. So during this section, we would say the object is melting, which means at this section, we have actually solids and liquid water right here. Some of the object is still ice, but some of it's melting into water. So there's actually two states of matter right here at the flat line. And that would be melting. This is always melting if I'm looking at a heating curve going up, because I'm going from solid to liquid, and that's always melting. For the one higher up here, I'm going from liquid to gas. That's called boiling. So up here, I also have two states of matter, and those two states of matter would be liquid and gas. So that would be like you boiling a pot of water on the stove. You still have liquid there. It doesn't just go poof into steam. That would be kind of crazy. There's still liquid water, but there's also gaseous water, steam, floating above it now, obviously boiling. Okay? So, again, let's go over this. There's only one state of matter at each of the quote-unquote curved lines, even though it's going to be a straight slope. There's only one state of matter at each of these curved parts, slope parts. And there's two states of matter at the flat lines because that's where a phase change is occurring. So the other thing we just have to kind of show with this is, why is this a flat line and why is that a flat line? Because when you are going through a phase change, okay, when you're going through a phase change, the temperature stays the same until all particles change state. All right? That's why if you have ice water will be at 32 degrees Celsius and will just stay at 32 degrees Celsius. Okay, so, oh my gosh, sorry, 32 degrees Fahrenheit. 0 degrees Celsius, 0 degrees Celsius. It'll stay at 0 degrees Celsius. I'm so sorry. All right, when you boil water, it will stay at 100 degrees Celsius. Got that one this time. All right, 100 degrees Celsius until all the water has boiled away. All right, so the temperature doesn't change at all. All right. To get more technical with it, which you don't really need to know so much in physical science, all right, is what's going on is the energy is being used to loosen what are called intermolecular forces. Intermolecular forces. That's at melting. Boiling, there's always a longer flat line because in this one we are breaking those intermolecular forces. IMF is short for intermolecular forces. So boiling always takes longer because you have to completely break all of the forces, the intermolecular forces that are acting between water molecule and water molecule. Well, from solid to liquid, the objects go from just vibrating in place to being close, but rolling around each other. You loosen them up, is the way I like to say it most. All right? So that is the main things about a heating curve. So you could have another heating curve where they might say, 75 degrees is when the object boils, and 25 degrees Celsius is when it melts. What should this look like? Well, I put in 25 and I put in 75. I should actually have a line that goes up at 25. That's where it's flat. Then it goes up, then flat, and then up. And I could go, where's a solid? If I label this A, B, C, D, E. Which letter represents solid? Solid is at A because B is the melting point. Anything below the melting point is solid. Where is the gas? The gas occurs at E. That's where it's above the boiling point. Where is boiling occur? Boiling's occurring at D. Where is liquid? Liquid occurs at C. Where is melting? Melting occurs at B. Where do I have two states of matter? I have two states of matter at B and D because those are the phase changes. When do I have one state of matter? I have one state of matter at A, C, and E. The temperature goes up for this because all the particles are the same. They just start vibrating faster and faster and faster and faster until they might break apart. Okay? The last thing I just want to quickly show you is you might see this sometimes as what we call a cooling curve. A cooling curve. It's just the opposite of a heating curve. You start at the top. Temperature. Temperature, time, degrees Celsius. You just start up high. So I'll do a cooling curve for water. Cooling curve for water would start up there, then go flat, then go all the way down to 0, go flat, and then go below. This is where gas is. This is where now condensation is. Then we have liquid. Then we have freezing because we're going backwards. And then we got solid. All right? So that's what you might see, a cooling curve, which is just the opposite of a heating curve. And that's pretty much it. All right, thanks.